This is my first time as a speaker at LCA, so I'm really excited to be here. And I thought I'll try and make a good impression and talk to you about the two things that I'm really passionate about, which are science and technology. Luckily for me, I get to combine the two a little bit for the kind of work that I do. So in this presentation, we're going to see why do we use containers for data science, and the case study of how do we use containers to analyze climate change impact in New Zealand crops. Before we begin, I thought I'll tell you a little bit about me and who I am. A bit of a disclaimer as well, because I am most definitely not a scientist, but I always wanted to be one ever since I was a little boy, like in the picture. Which is, by the way, the only good picture I have of me, so there you go. So I always wanted to be a scientist, but instead I ended up working as a sysadmin at a company called Plant and Food Research, which is based in Auckland, but we have sites all over the country. In Plant and Food, I sort of help the scientists with the projects that they have, and I thought, well, it's a little bit like the same. I mean, I'm not a scientist myself, but I get to work with them, so it's kind of cool. It's also a bit sad sometimes because, you know, they keep reminding me that I'm not one of them, so eventually I had to find a way to cope with it. Anyway, in Plant and Food, as I said, I work for them, and what we do is basically we are a Crown research organization. That means it's a New Zealand-owned organization, but we operate as a private company, which means that more than 50% of our funding actually comes through commercial contracts rather than taxpayer money. And I think that's a really interesting model to operate under. These are some of the locations for the 14 sites we have in New Zealand and a few offices we have overseas. And the last time we counted them, I think we had a little bit over 1,000 employees. And believe it or not, a few of those are actually scientists. The kind of activities that we do, we sort of focus on the agricultural and seafood industries in New Zealand. And we provide scientific research that enhances the productivity of their production lines, as well as the quality of the produce we then hopefully export, and we try and capture the premium market overseas. So these are some of the portfolios where we split up the kind of science that we do. I have been personally involved with the first two, new culture innovation and bioprotection, and quite recently, sustainable production. To give you a more concrete example of the sort of things that we do, who here has ever tried a gold kiwi fruit, the yellow one? Who here has seen one? Okay, a few of those. Did you know that Plant and Food actually developed the gold kiwi fruit that you can buy today in the market? We did that in a partnership with Zespri, who are basically the ones that have the monopoly on anything to do with kiwi fruit in New Zealand. And what you may not know is that it can probably take about 20 years of field trials to find the perfect fruit that you can then put out in the market. And this is looking for the fruit that has the specific traits that make the product valuable in terms of the flavor, the size, the shape, the sugar content, those sort of things. And with the science that we do, we can cut that research time down by approximately 75%. So we can break the time down to market to maybe about 5 years, which is a really good time saving. And the way we do that, particularly for NCI, or New Cultural Innovation, is to use bioinformatics to find the genetic markers that track those traits that we're interested in. And then rather than growing a whole bunch of different cultivars, we just focus on the specific varieties that promise to express those traits that are interesting. The job that I do in particular, I'm basically responsible for the high-performance computing cluster that scientists use to run their research on. And part of being responsible for this environment is that I get to not only do the cool things like racking and installing equipment in the data center, I also get to manually compile and install hundreds of different pieces of software tools that the researchers use in production, and these are typically written by third parties. I think that the way that we use technology is slightly different from the vast majority of companies out there. Typically, you use IT in any organization as some sort of ancillary service just to increase your productivity, and things like email and video conferencing are prime examples of this. Or technology is your product. You're actually creating a software solution that you sell to your customers. But in our case, we are sort of like in between. We use software to do research, but we don't necessarily sell the software itself to the consumers who actually sell the research. And this leads me to one of the most important things about the metrics that we use to measure the quality of what we do. It's not necessarily uptime, it's whether the research that we do is reproducible or not. Reproducible research is one of those fundamental concepts in the scientific method. It's the idea that anything you do must be able to be replicated by someone else, provided that they have access to the same input data and, well, the methods if you documented them. And over the years, I came to realize that there are a number of obstacles to reproducible research from an IT perspective. These are some of them. Dependency hell in particular is a problem that predates all areas of IT, not just computational science. But some of the other obstacles are also specific, and you can sort of see them in really, really clearly for scientific software. Poor code quality or bespoke installation methods are quite common. And let me illustrate this with an example. I'll take you through a typical day of my work. So some scientist comes to me and says, "Hi Eric, can you please install this software tool for me? I need it for a research project that I'm working on. Here's the GitHub URL." And I go and then look at the readme.md if there's one, and it says, "Oh, just run setup.sh," which will automatically download all of the dependencies and put them in your home directory. And I need to hack that because obviously multiple people are going to use this in the cluster. So I go, okay, just give me a couple of days. I'll figure this out and I'll get back to you. So I go on, I deploy the tool fully integrated with a cluster, ask the researcher to test it, and then they come back to me and saying, "Sorry, it doesn't work, please fix." And typically, that's as descriptive as a bug report that I get. So then I have to chase them out and see what does doesn't work actually mean. And I'm not going to shame anyone or any particular project or person, but this is an example of the sort of things that I tend to deal with. If you can read it, it's someone that hard-coded a path to one of the dependencies in their scripts. And this is an issue that was open on GitHub in 2015. It's still open. The screenshot was captured not that long ago. And obviously, this means that they're not taking pull requests. But it doesn't end there. The guy that reported it just kept going and finding different hard-coded paths all over the place, to the point that he basically gave up and said, "I'm not sure if I want to keep chasing this anymore because it is clear that whoever released this didn't even bother checking that it ran." Which I think is ironic because when I was testing the tool, I realized that it had to go to the legal department, obviously before publishing, and they forced the author to put this really large copyright banner on every single piece of code that he put on GitHub. And then all of the scripts failed because he didn't even bother commenting that out, and you get a whole bunch of syntax errors. So over the years, this has obviously taken a toll on me, and I think it shows because that's me when I first started working, and this is me a few years after. So, you know, it's a bit frustrating at times, but the reward is that when I do actually get things sorted, I actually help scientists get on with the research, which is actually really rewarding. Which leads me on to the climate change project that I've been involved. A couple of years ago, this guy called Edmar, who works down here in our Lincoln campus, not too far from Christchurch, came to me and said, "Hey Eric, can you please help me? I'm working on a project that deals with climate change." So naturally I said yes. And I asked him to explain to me basically what he does, because he was from a team that I never had to interact before. And Edmar is a systems modeler. He basically looks at how different variables affect the growth of different crops that are of interest to New Zealand. And they use crop simulation models to do that sort of research. The way this works, and again, I'm not a scientist, so this is a sort of layman's explanation, is that they grow different plants under controlled conditions. They measure the effect of different variables to the growth of the plant, and then they quantify that, putting that into a model that you can then use with software to simulate what happens if those conditions change. There are a number of different variables that you can take into account. And they range from anything related to the weather, the soil, the terrain, any management techniques, whether you add fertilizer or not, whether you irrigate or not, and many, many more. But the point here is that for every single one of these that you want to change, you need to run a full set of simulations to see how those variables correlate to each other. This is the reason why crop simulation is typically done at a small scale. We're talking a few plants or maybe a tiny area in a farm. When you want to go up to a larger scale, you typically don't even have the data sets necessary for every single one of those variables to analyze this at a really high resolution. So what you tend to do is to grab the data you have and then upscale or downscale that data to the resolution that you're interested in. When you want to do large-scale analysis, like on a regional or a national level. You can think of this process the same as when you zoom in or you zoom out on an image. You can go in as much as you want, but at some point you start seeing pixels. Or you can zoom out as much as you want and see that you lose some of the fine details. And what this does is to introduce uncertainty in the resulting models. So you cannot really trust the results of the simulations at the same resolution as if you were doing it on a small scale. Edmar's project in particular was quite ambitious because he wanted to model the impact of 100 years worth of climate change simulations across the entirety of New Zealand. And in his prototypes, what he was expecting to accomplish is something like this. This is all based on simulated data. What this is showing is how much maize in particular you can grow in New Zealand based on the current weather versus future weather. I believe this is 100 years from now. And that clearly shows that the further south we go, the more yield we can get compared to today in a possible future. And not only this, he also wanted to do this at a really, really high resolution for the entire country. And the resolution that he was targeting is a 5 by 5 square kilometer grid. We're talking several million simulations here. And each simulation takes about 10 minutes to run on a single CPU core. And here's Edmar's problem. System modelers tend to use Windows to do their analysis because Absim runs on Windows. And hopefully they're not using XP anymore, but that's the screenshot that I got from the documentation. And the problem that Edmar has is that if he were to run his project on a Windows desktop, or a Linux desktop for that matter, you're constrained to the computational capacity of the hardware. So it's probably faster to just go outside and see what happens. So I thought, okay, well, definitely can help you with this. Obviously, we need to use HPC for this. But I don't really want to maintain a separate Windows cluster, mainly because I know nothing about Windows. So he said, no, don't worry. Absim actually runs on Linux. The guys that developed it, which are CSIRO in Australia. CSIRO is the Commonwealth Scientific and Industrial Research Organization. They run this in their cluster on Linux. So we can probably just grab a copy of what they do and then just run it on ours. And because it's written in .NET, you can just use the Mono framework to run this on a Linux platform. And I thought, okay, let's go to the Absim website and see if we can find a binary release or an RPM or something that I can just use. And obviously, they don't have any. They have a few older releases, but not any of the new versions. No problem, we'll just compile one. And well, if you can read, it didn't actually give me a good start or a good feeling when I started. The compilation process is basically just follow what you would do for Windows, but replace .exe with .sh, which isn't a great start. And it also says these instructions pertain to the Ubuntu 12.04 distribution, which is what, now, 7 years old? And then it just goes on and lists a few, not all of the dependencies that are required to compile the tool, let alone run it. And I thought, okay, well, we run CentOS 7, we need to find what are the equivalents of any of this to even start compiling the tool. So I keep going, and then I see that I also need to install the R, statistical programming language, and a few of the packages that come with it. And I included this bit because I just love it. It says, Absim is a mix of native and .NET applications. Each runtime has a few peculiarities that might be addressed. And then it doesn't go on telling you what those peculiarities are or how to address them. So, you know, fun times. And I thought, okay, these people are literally across the ditch. I can just talk to them. I'll send them an email and see if they have an internal release that we can just, you know, copy from them. So this is the reply from one of the developers. It's highly redacted to protect the innocent. But he basically said, look, we don't provide any binary releases for Linux because, well, no one is interested in them. If you want to compile one yourself, bear in mind that you need to load this kernel module to make the mono assemblies actually executable. Rather than prefix them with mono every time. And try not to use the latest version of mono, maybe stick to one of the older ones, the new ones will probably give you trouble. And I thought, okay, this is a little bit beyond dependency hell. This is integration hell. And luckily, this is a problem that can be solved with the same techniques as you can solve dependency hell. And you'll know what the solution is. It's in the title of the talk. What did we do to fix it? Yes, we put it in a container. It's simple, right? Now, if you think containers, you're probably thinking Docker, and fair enough, they're the ones that basically made containers famous. So naturally, this is the first thing that we try. We try and put apps in a container, mainly to see if it was possible. And the thing that we quickly realized is that leave alone the fact that I don't really want to give data scientists root access on the entire cluster. Running Docker in a multi-tenant environment is also quite cumbersome. And I'll put you in the shoes of a data scientist for a moment. Imagine that you're writing a script to analyze a lot of files using Docker. So you start off with the best shell that has ever existed. You then go to where you have the input files, and you open a for loop. And you type in the command that you use to send the jobs to the job scheduler, and then the Docker run. And notice that immediately we start adding weird flags like that -u over there. The reason for that is that in a multi-tenant environment, you don't want the containers to run as root, so you have to specify a user. And even if the container image has a non-privileged user specified in there, you want the results that are going to be written to the persistent storage to be owned by you, not someone else. So you have to specify it in -u. You also want to give your containers a name. And this is not just for your own benefit, so that you know which container was processing what. It's also in case that someone else has access to Docker in the cluster and goes, who is this whimsical Einstein or whatever, and then, nah, and just kill it. So it's also to warn others that this is a container that you actually started. You also need to mount the persistent storage into some location in the container, doesn't matter what. And if you're running Red Hat or CentOS, you need to mine the Linux. And finally, you specify the container image, probably from a private registry, and the entry point arguments, like the input file that you want to analyze. Now, we just flew through all of that, and hopefully most of you understood what I meant by any of those lines. But the reason we can understand it is because we sort of live and breathe this stuff all day. How easy do you think that for a data scientist this is, particularly one that has recently just moved from a Windows platform to a Linux one? It's a lot of complexity for them to absorb. So obviously we had to find a solution for this, and we started looking at alternatives. We found this container engine called Singularity that promises to solve the problem because it's targeting particularly HPC environments. And let's look at how Singularity simplifies this. And that's a much more clear way of running containers. Notice that there is no specification of the UID. Singularity does not let you run containers as anybody but yourself. There are no daemons or no privilege escalation allowed. You also don't have to specify the mount points that you want to map to the container. You can if you want to, but by default, the /home/tmp/dev and a few other mount points, including the ones that the sysadmin configures, are pre-mounted on any container that you start. And also, you can just run the container image directly. It's a single file that you can then distribute alongside the input data, and you can, when you execute it directly, you just run in the entry point. So you can pass on command line arguments to it as well. If you want to build a Singularity container, you have two options. You can either create a recipe file, like a Docker file, except you call it Singularity, because why not? And then you just issue a Singularity build, and the name of the image, the results. Or you can just pull it from a Docker registry. And what this will do is to just flatten all of the layers that are contained in the Docker registry and store that as a single file that you can then just execute. So Singularity is really cool as a solution. These are some of the main differences that I just mentioned. And I will say that if you have a use case that is similar to this and you want to run containers without giving root privileges to your users, then don't look at Docker, look at Singularity. It's a really cool project. So in the climate change project, back to the science aspect, we needed to grab data sets for the entirety of New Zealand and a lot of the variables that we wanted to play with. So we talked to the people from NIWA. This is the National Institute for Weather and Atmospheric Research in New Zealand. And they provided us with simulated climate data sets for up until the end of the century. And we talked to the people from Landcare Research, which are another CRI. And they provided us with access to a tool that they just released called SMAP, which maps out the soil information for the entirety of New Zealand, as well as the terrain detail. And we, as Plant and Food, provided obviously the crop models that we're interested in. We pre-processed all of this using the R statistical programming language and created a whole bunch of AppSim files that we can then run at scale in our cluster using the container images. And we post-process the AppSim results into a PostgreSQL database that we can then visualize with a web application that we're also writing. The entire pipeline has been documented in a Jupyter notebook. And if you don't know what Jupyter notebooks are, they're basically a IDE that you can sort of use on your browser to type in code and comments in Markdown on the same document. And you can execute the code directly on your browser. In our HPC cluster, we provide Jupyter Notebook servers that are connected to the cluster itself, so the users can just run the jobs in the cluster directly, which is really cool. And the other advantage of using notebooks is that they're effectively a JSON file. So you can just put that into a version control using Git, and then anybody that works in the project can just Git pull the latest version of the pipeline, which is really cool for collaboration. The web application that I mentioned, this is a screenshot of the prototype that we're currently working with. And what this is showing is basically what you can do with the application, which is to compare one reference scenario and one alternative scenario. So the top maps on the left and right show basically, in this particular case, we're looking at the yield of maize in the Hawke's Bay area, depending on whether you rely on irrigation or rainfall. And the maps at the bottom show the difference between the two scenarios, as well as the regional distribution for either one of those. If you zoom in, you can see the 5-kilometer square grid that we're targeting. So this can be done at a really, really high resolution for the whole country. And this is another screenshot that shows the climate change impact now, actually for real, looking at the yield of maize for all of New Zealand, which sort of matches the simulated model that we had at the beginning. We can see, hopefully, you can see from back there, that the left-hand side is showing the current weather. The right-hand side is showing the future weather. This is the most extreme CO2 emission scenario. And what this image shows is that on the North Island, we basically drop a lot of yield, but we regain that by quite a higher factor in the South Island. So based with this information, we can probably advise the producers to either just sell out and move to the South Island, or to maybe start harvesting the crop earlier as the warmer temperatures start a little bit earlier in the year. So where to from here? Well, obviously we need to continue refining the web application, which is written in Shiny, by the way. Shiny is a framework for writing applications based on the R programming language. And we're not super happy with the UX. I think it's still a little bit quite complicated for a user to build the scenarios that they want to compare, but we'll hopefully get there. And the other thing that we need to do is to just run all of the simulations, which is easier said than done, because the cluster that we have, as much as I love it, only has finite capacity. And it's a shared resource, which means that we cannot just use it for this project alone. There's a whole bunch of other groups that also have to use it, competing for the capacity that we have available. So potentially one of the other things that we could do in this project is to maybe become a little bit job scheduler agnostic and try and get capacity from wherever we can get it, which would also include things like the public cloud if we can ever get funding to actually pay for it. And also that will mean solving the data gravity problem, because I mentioned that the data sets that you need to have are really, really large. These are currently stored in our cluster, taking up quite a lot of space. And if we were to just move that to the cloud, that would include quite a lot of cost for keeping it there for the time that we need to run this analysis on. And I think that for a project that is effectively not going to create a product that is just going to be sold to anyone, this is probably one of the largest obstacles. It's research that is done basically with the funding that we get through grants, and that's it. So we basically are constrained to the capacity that we can make available with the little funding that we get. Before we finish, I wanted to sort of go back to the idea of containers and reproducible research, because I think they're a really, really good fit to achieve it. Containers give you portability, because once you create the container image, you can just distribute it whatever way you want. It also gives you immutability, which means that once the image is created, the only way to change it is to just create a new one. And it allows the whole process to be reproducible. The container images can be created on a deterministic fashion, provided that you follow best practices when you're creating the recipe file. So the last thing that containers provide as a benefit is that you can scale the analysis out. So long as you can run containers in the platform that you're running your analysis, you can just grab the image that you use to process the data and then scale it out almost unlimited. I do like the fact that things like AWS now provides a solution called AWS Batch that you can use to run containers at scale. They don't support Singularity yet, they only support Docker, but hopefully that will change in the future. And the other cool thing about Singularity in particular is that because it doesn't run as a daemon, you can simply just compile it and then distribute it and just run it as is. So it's a really good framework to use for computational science. So that's all I have, unless you have any questions. Thank you for your attention.
Questions on containers, probably not questions on climate change.
I'll try and do a little bit of both.
Hi, thank you, Eric. Have you done any work with GPUs in Singularity?
Well, Singularity containers mount /dev to the containers that you start. So you can definitely have access to any specific hardware that you want, including GPUs. In fact, NVIDIA recently released a product called Container Maker or something like that can create both Docker and Singularity containers using GPUs, obviously, to run analysis. They're really good for machine learning as well.
Have you not got to tie up the driver versions between the image, Singularity, and the system driver as well to make it work?
Sorry, can you repeat the question?
Sorry, have you got to have the same NVIDIA drivers on both the container and on the system for it to work?
No, you don't, because okay. the host is the one that needs to have the drivers installed. The hardware is exposed to the host. So long as you can mount the /dev tree onto the container, you can access the hardware that you have available on the host directly. These are all of the people that have been involved so far in the project, by the way, so and credits.
Sorry, quick question. I was just wondering if you tried Red Hat's Podman and Builder tools in replacement for Docker and Singularity.
Funny you mentioned that, because the last couple of months I've been away while Podman was released, so I didn't have a chance to test it out yet. But I did open a feature request recently to get multi-stage builds in the version of Docker that it comes with Red Hat, and they came back to me saying, "Oh, check out Podman, which already does that." I thought, oh, okay, cool. I didn't even know that existed, but no, I haven't yet. I will definitely soon.
With regards to the AWS side of things, as it's predominantly Kubernetes based, what's the limitation on Singularity, considering Singularity works just as well with Kubernetes as Docker and Rocket?
So Singularity and Kubernetes is something that I'm still yet to explore. I know that there's work that Scilabs, who develop Singularity, are doing to integrate it in the Kubernetes model. That said, I'm not sure what the status of that is, and I think that there's still quite a lot of work to be done to actually get it to work. If you want to run Singularity containers in AWS, all you need to do is to just spin up an instance with Singularity installed in it. So that's the other way to go around it. Now, you could do this with spot instances and try and minimize the cost, but that doesn't really solve the problem of having to put all of the data in AWS if you want it directly accessible, or opening up a tunnel to your local storage and allowing the AWS instances to talk back to our data center. Particularly for New Zealand, that's actually quite hard, because the closest POC that we have with AWS is Sydney. So we need to rely on the RIANS tunnel that talks directly to them. And we haven't actually tested yet to see whether the latency affects the processing time and whether that's going to be more cost efficient or not. Cost is also obviously one of the main drivers, so there's a few obstacles there, but again, it's the next phase of the project. The first one at least has already been completed.
Any more questions? Going once, going twice. Thank you very much for that great talk. And I will give an extra shout out to the greatness of having a credits reel of people involved in the project for your own future talks, folks.